Okay, very welcome to all of you, and we will be proceeding our talk on integral quantum Hall effect. And I think we have gone through the introduction of this very important experiment that was performed in 1980 by von Klizzing. And before proceeding for the mathematical treatment of integral quantum Hall effect, I would again love to remind you the very important outcomes of this result. And if I rightly go back, what we have is we have a two-dimensional electron gas, and what you do is you suspend the set of electrons in two dimensions, and then you apply a very, very strong magnetic field, and you lower down the temperature of the system. When you lower down the temperature of the system and you increase the magnetic field, you are able to see the strange quantum mechanical behavior of your sample. So what does that mean? That means your two-dimensional gas can be treated quantum mechanically, because the results that you obtain here, the very astonishing result is there that certainly might have flabbergasted von Klizzing when he might have observed the result where you have the quantization of resistance in XY direction of your sample. And at the same time, what is happening is you have the longitudinal resistance. This longitudinal resistance is immeasurable, but at the point of the plateaus, at the start of the plateaus, there is a sharp rise in the resistance. There's a sharp rise in the resistivity. Okay, so what you see your longitudinal resistivity is almost zero, except at the point of transition, where the resistivity makes a transition from one quantized state to another quantized state. Now, what could be the basic explanation from quantum mechanical point of view to this problem is that what you are doing is you are subjecting this two-dimensional gas to a very strong magnetic field. And when you subject it to a very strong magnetic field, what would you expect? You would expect the orientation, the motion of the charged particles, right? The circular motion of the charged particles. And if you imagine the circular motion of the charged particles, assuming them to be electrons, the middle portion of your sample will behave like an insulator, because there is no net flow of electrons. But when you think about the edges of the sample, at the edges, the electrons will not be able to make the complete circles. At the edges, you will have semicircle movement of the electrons. And this semicircle movement of electrons gives you the current. And this is also called as chirality. Now, what is happening basically here? What is happening when you are applying the magnetic field? When you apply the magnetic field, you have certain observations. And these observations are a result of quantization. And the quantized levels that you have in your sample, it's not a one particle system, okay? You have billions of particles in your system, right? And what comes out here in presence of magnetic field is what is called as Landau levels, okay? So you have the quantization of the energy of the electrons, okay? It's not one electron, it's a set of electrons. And on applying the magnetic field, what happens basically, in each Landau level, you have degeneracy. We understand degeneracy from quantum mechanics point of view, okay? And what happens as you keep on increasing the magnetic field, the inner levels of Landau levels, they all get occupied. The moment Landau level is completely occupied, there is a transition to another Landau level, okay? In the similar way, you have, as you go on increasing the magnetic field, there is filling of these Landau levels. So where from these Landau levels are coming? They are coming because of magnetic field, okay? And they are coming from very, very strong magnetic field that's acting on your system. And your system must be at very, very low temperatures. So what is happening here? What is happening? You assume to model this problem by assuming non-interacting electrons. There are tremendous number of electrons in your system, but these electrons are assumed to be non-interacting. They are not interacting with each other via electrostatic interaction. And presumably coming to the fact that these Landau levels that we have, which are coming as a consequence of the variation in magnetic field, what you have is you have those patterns of resistivity, because now you have a very, very fundamental quantity. A fundamental quantity like resistance, which you are writing in terms of the very fundamental constants of nature. As I said in the beginning, that the resistivity in xy direction is h by e square k, where k is an integer. So that means these plateaus that you have, these plateaus that you obtain, okay, you have a plateau. So for the plateau, you have Landau levels, okay? But as you increase the magnetic field, these Landau levels are filled by the electrons. Are you getting my point? Once this Landau level is filled, you have a transition, okay? You have a transition and you have a next level of quantized resistivity. Are you getting my point? Okay? So this is the story of integral quantum Hall effect. So if we quickly go for the introduction here. What we have a two-dimensional electron gas that I have talked about, that how we achieve this two-dimensional electron gas in terms of gallium arsenide sample that was used in the original experiment. And what happens here? Your Hall resistance, it becomes quantized, okay? The resistance becomes quantized. That means you have a more fundamental constant of nature. This is used in metrology. Now you have a very standard unit of resistance in terms of the Planck's constant and the charge of electrons. Okay? So the origin, as I said, electrons form what? Discrete energy levels called Landau levels. Clear? Okay? Under very, very strong magnetic field. So you can expect this kind of thing only when you are able to place your sample in a very, very strong magnetic field. So when these levels fill completely, Hall resistance forms quantized plateaus, as I said, okay? So you have the quantized plateaus. Importance, okay? It provides an extremely precise and standard for the electrical resistance. So you are taking it as you take in classical sense 1 kilogram, okay? So for you have those isotopes of carbon atoms taking as very, very standardized units of mass. Here you have a very standardized unit of resistance in terms of H and U, and which certainly becomes a foundation for topological physics and modern condensed matter physics. So it has a very good connection with the technology. It's used in calibration of resistance, okay? You can calibrate resistance using this H by E squared, okay? So certainly it does influence the very research that's going on in the field of graphene or carbon nanotubes. So it has its role in graphene electronics, quantum devices, and topological materials. This is your graph, okay? And this is your sketch. What you have is, you have these kinds of plots, and each plateau is in the form of h by e squared times k, and k is an integer. This is a very rude kind of graph. This is not basically what was achieved. In fact, it's a very complex kind of graph that was obtained in the original experiment, but this is what we are trying to give the idea about. Okay, so you have two types of resistances. What you have? Okay, you have two types of resistances. Can you tell me? You have two types of resistances. One is rho xx, another is rho xy. In the previous case, we were discussing about the classical treatment of our problem. Okay, so today we will subject it to the quantum mechanics, and we would like to discuss on this very problem in detail. So what we have had, we had a very first thing. What was that? That was, if I say this sigma xx is equal to 0. Okay, and you have rho xx equal to 0. And for sigma xy, we have minus 1 by rho xy. And this is something, what is sigma xy will lead us to minus k e squared by h. It's not h bar, it's only h. Okay, so this is your conductivity in xy direction. And talking about these two is basically that how this two-dimensional gas will behave at these two points. Now, if I say that sigma xx equals 0, what does it mean? It means your sample is going to act as a perfect insulator, right? As I told you, if we go back to that two-dimensional kind of gas, what you're doing is you are applying a very, very strong magnetic field. What you expect to these electrons is they will make the loops in the middle of your sample, okay? So you will have no net flow of the current, right? But on the edges, the electrons will only mark the semicircles. So you will have the conduction. So in the middle of the sample, what you are expecting is it will behave like an insulator. Okay? And this flow of current on the edges, we call it chirality. It's called as chirality. All right. Okay? So what we have, if I talk about the tensor of the electric field, okay? Electric field, if I write down it as its components as Ex and Ey, and using those conditions, we must have 0, rho xy, and minus rho xy, and 0. Okay, I can write down this electric field as the product of this Jx and Jy. Okay, so what will you achieve by multiplying these two? What will you obtain from this? This will give you 0 and rho xy and Jy. Okay, so here you will obtain rho xy and Jy. For another term, you will have minus rho xy and Jx. Now, what does it mean? It means that the dot product of electric field and the current density is equal to 0. Can you tell me what this dot product of electric field and current density is? Yeah? It's work. It's work. So when you have the dot product of electric field and J equal to 0, what it means? It means no work is done. If no work is done, how you can have current? Can you have current? You can have current. Yeah, what kind of current we will have here? We will have steady current. Right? So E dot J equals 0. It reflects the fact that you have a situation where there is no work. The work is not done. So that means if the work is not done, you don't have a current that's there because of the potential difference. You have a steady current, okay? And you have a steady current in your two-dimensional gas. This is an empirical approach to realize these plateaus that we obtain in our experiment, right? But now we would like to subject this problem to the quantum mechanics, okay? When we subject this problem to the quantum mechanics, we would like to see how we can treat Schrodinger's equation when we are dealing with this two-dimensional gas of electrons, right? So if I have to go for the quantum mechanical treatment, I have to realize the very first important information about this system is that I'm applying an very, very strong magnetic field to my sample. That means your Schrodinger's equation has to be subjected to that external magnetic field that you are applying to your system. But from the knowledge of electrodynamics, you can write down magnetic field in terms of a vector potential. And to be precise here, Schrodinger's wave equation is gauge invariant.
Yes.
Now, what do you mean by gauge invariant? How can you express this reality? What do you mean by gauge invariant?
जब हम किसी भी फिजिकल क्वांटिटी पे अप्लाई करेंगे तो दोबारा वही वापस आएगा. For example, जब
Exactly. How can you demonstrate that for this problem? Okay, that I can do, as you said, okay, you're right. As you said that if I have the magnetic field B, right, I can write down this magnetic field as the curl of a vector potential A, right? This is what we can do. And what I said is, when you are applying the magnetic field, it's perpendicular to the plane of the electron gas, okay? But you are trying to write down this magnetic field due to a vector, what's called as vector potential. Are you getting my point? So, what am I saying here is that you have to realize that Schrodinger's wave equation is gauge invariant, right? What does that mean? That means this vector potential, A, I can write it as A1 plus or minus, depending on your situation, plus minus gradient of some
function f,
some scalar term, isn't it? Now, if I take the curl of this equation,
yes,
what will I get? If I take the curl of this equation, what you are expecting, you will have the curl of A will be equal to curl of A1 plus curl of gradient of chi. But what is curl of gradient?
0.
That's 0. So you have the invariance.
Yes.
You have the gauge invariance. That means you can select A in terms of B, and you can choose the coordinates. Okay? If you choose, say, for the sake of argument, if I choose the coordinate X, or I choose a coordinate Y, in the two-dimensional plane, I will get the same thing, isn't it? Okay, this is what is called as gauge invariance. So this we have to keep in mind while we proceed for the discussion of quantum mechanical treatment of this problem. Okay, so let me go on now. Now what should I start with? I should start with the Schrodinger's wave equation. So what is Schrodinger's wave equation? It is the Hamiltonian operator acting on psi, x, y, and z equals E psi, x, y, and z. Am I right? This is it. But my problem is I am treating non-interacting electrons and I'm assuming that the potential faced by these electrons is 0. So what is your H? H is minus H bar square by 2m del square psi, which is a function of x, y, and z, plus v as a function of x, y, and z. This is my Hamiltonian, right? But the potential part of this Hamiltonian is equal to 0. So H is going to be this thing, right? So I'll be writing this. What will I write here? Come on. I'll be writing minus H bar square by 2m. Then I'll have del square. Then I will have psi of x, y, and z. And this must be equal to what? This must be equal to E psi x, y, and z. Isn't it? Clear? But this is your Laplacian operator, and I can write down into the three very important components. So what will I get from here? I'll get minus h bar square by 2m dou 2 by dou x2 minus h bar square by 2m dou 2 by dou y2. It has to be minus, okay, minus h bar square by 2m dou 2 by dou z2. Okay, this will be multiplied by psi x, y, and z equals E psi x, y, and z. Isn't it? Now, you see, this is h bar square by 2m. Del square by del x square. What is it? It's the square of momentum operator, okay? Isn't it? But here, I will be using P and I'll put a line here. So you should realize that P is an operator, isn't it? So how will I write down this equation? Come on. How will I write down this equation? Yeah, you will have P x square by 2m plus P y square by 2m. This line is indicating that it's an operator, okay? Then plus P z square by 2m times psi x, y, and z is equal to E psi x, y, and z. I'm applying the magnetic field in the z direction, right? So, because my problem is two-dimensional in nature, and on applying the magnetic field in z direction is a reflection of electron will have free motion in the z direction, right? So, assuming that thing, we can take off this component from the Schrodinger's equation. Okay? So there will be no momentum along z direction. What will happen? Your Schrodinger's equation will boil down to two-dimensional plane because that's my target. Okay? But what am I doing? I'm canceling the third component. Okay? And assuming that that's the direction of the magnetic field that I'm applying on this gas. So what do we expect now? So what we get from here is Px square by 2m plus Py square by 2m. But now your psi x, y, z will change to something else, phi xy. And you will have energy eigenvalues as, I will call that E1 phi xy. Are you getting my point? Right? We are taking our system mathematically equivalent to this two-dimensional gas.
Yes.
Isn't it? But this is your Schrodinger wave equation without applying the magnetic field. Okay? I chose the very assumptions, but what you are doing, you are applying magnetic field. So applying magnetic field is going to change.
सर ऊपर इस साई है इस xy ऊपर
Yeah.
Yes.
इस साई है वहाँ पर
Here. Yeah, this is psi. For all the three components, okay? But here, because I'm losing the z, I'm changing it to another eigenfunction as phi of x and y, isn't it? Okay. Now, let me write down. So what's going to happen is, you will have the change. What I have p x. And this px will have a change, minus EA. Well, A is what? Yeah, what is A? A is the vector potential. Divide by, this is whole square. Divide by 2m, right? Plus Py square by 2m. Isn't it? This is all multiplied by phi of xy equals E1 of phi of xy. Are you getting it?
Yes.
Right?
Yes.
Okay. Now, what I have, A is the vector potential. But A has a relation with magnetic field. Right? A has a relation with magnetic field. And what is magnetic field? Magnetic field is the kernel of this A. But A can exist in X and Y. Are you getting my point? Are you getting my point? Now, if I choose this AX is equal to minus BY. See, I told you, Schrodinger's wave equation is gauge invariant. So it's your choice, okay? Now, if I choose this AX is minus BY, this is called Landau gauge, okay? What is it called?
Landau gauge.
This is called Landau gauge. Choosing what? AX is minus BY 0, 0. The other two components we are choosing as equivalent to 0. You can have other choices also, as I said, because Schrodinger's equation is gauge invariant. And the vector potential that you have chosen here, you can choose it other way also. That's why you can find different things in different contexts. Choosing it like this, choosing it like AX equals minus BY is something called as Landau gauge. So what gauge we are choosing? We are choosing AX equals minus BY. Clear? Okay? So this is what is called as. So Landau gauge is nothing. It is just choosing a special one that works in your problem. Right? See, what is the motivation here? We are coming from a three-dimensional Schrodinger's wave equation, and we have the circumstances in our experiment. We want to boil down this Schrodinger's equation to one-dimensional problem. This is the target. Are you getting my point? So what am I trying to tell you is, you have this thing, when you will substitute this thing, what you will obtain from this. But before what we obtain from this is, you have Px and Py. This Px, it commutes with the Hamiltonian. What happens to Px? Px commutes with the Hamiltonian. So if it commutes with the Hamiltonian, It's equal to 0.
Yes.
So if Px commutes with the Hamiltonian, this commutation results in constant momentum along x. What? Constant momentum. See, you are turning a very, very important part of the equation into just a number. Px commutes with the Hamiltonian, and when an operator commutes with the Hamiltonian, what it will give you? It will just give you a number, right? So there is a commutation between Px and h. So your two-dimensional problem is boiled down to one-dimensional problem. Okay? So when we use these approximations, what we obtain is we obtain Py square by 2m plus m by 2 EB by m y minus y naught whole square. It was psi, then it was phi. Now I will call it f of y equals e2 f of y. While this y naught is, I'm not sure, it is m by eb. Now check it. What you have, this is everything in terms of y. And y naught is the only thing, I was telling you, this y naught is px by eb. Well, this y naught is the only thing in terms of x. But px is not a function. Px is just a number. Can you tell me what is this? Can you sense it? Doesn't it look to something usual that you have done in your basic quantum mechanics course? Does it resemble with something like that? Come on. Hey, come on. And you have solved it. It's a differential equation that represents your harmonic oscillator in one dimension. 1/2 of kx squared. Isn't it?
Yes.
So it is a harmonic oscillator problem. And you know how to solve the problem of harmonic oscillator in one dimension. And when you solve the problem of harmonic oscillator in one dimension, what you obtain? You obtain the quantization of energy. And you will obtain the same thing by solving this equation. And what you will obtain from this equation is, you will obtain En equals n plus 1 by 2 h cross omega c. And what is this omega c? Omega c is called cyclotron frequency. Cyclotron frequency. And this omega c is nothing but EB by m. So the quantized energy that you will have, what will be that equal to? Yeah, that will be En equals n plus 1 by 2 EB h bar by m. Come on, look at it, okay? There's nothing to be taught because you know how to solve the problem of harmonic oscillator. It will take the same series kind of solution, all the solutions that you have used to reach out to this result. So what are you expecting here? You are expecting here n is equal to 1, n is equal to 2, n is equal to 3, isn't it? So what you are going to get? You are going to get the levels. N is equal to 1, n is equal to 2, n is equal to 3. And this is called Landau levels. Getting my point? Right? So your Landau levels have a dependence on the magnetic field. See, it's connected to a system of electrons. Right?
Yes, sir.
And it's telling you that as you increase the magnetic field,
Landau level.
you will have a quantized set of energies. Isn't it? Okay? And as you go on, you will have more and more energy levels filled. Are you getting my point?
Yes, sir.
Reflecting the very important fact that you have those plateaus that you obtain experimentally while performing this experiment. The way you have the quantization of energy, you will have a generalized wave function. What will be that? So that will be Fn of y equals 1 by under root of ax e to the power of I kx, and then you will have e to the power of minus eb by m y minus y naught whole square by h bar times the Hermite polynomial of eb by m y minus y naught. And you know all of the story about the Hermite polynomials. You will have odd and even solution for the Hermite polynomial, and you will have a complicated compressed wave function, the set of wave functions for the system of electrons living in this two-dimensional gas, isn't it? Right? Now you can proceed on from here yourself, where you can obtain that very important condition of plateaus. You will have to make a couple of assumptions, and you will reach out that resistance rho of xy equals h by k e square. That gives us an idea about the quantization of plateaus, the quantization of energy at that scale of measurements. Any questions? Any questions? So I thank you all. Let's stop here.